Now.
Great. All right. Welcome to the next edition of Hazel Park Amateur Radio Club Technician class. We are finishing up some things from Chapter 3, just a few things. And then Bob is going to take us up into the ionosphere and possibly down and play with some cables and transmission lines. All right. A couple of things that I have to finish up with. If you can go to 3-17, page 3-17, or if you have the Kindle, it would be chapter 3-3, radio circuits, and we got to talk about a couple things because they are on the exam. All right. Okay, one of the questions is, what's the name of a circuit that generates a signal at a specific frequency? Now, that thing is called an oscillator. Bob, do I have screen sharing privileges?
Yes, you do.
Okay, thank you. Okay. All right, see if I can. All right, can everybody see this thing?
It's coming up. It's not up yet.
Okay.
Okay, it's up.
It's up. Okay. What this is, I think you can recognize almost all the parts except for this. All right. Okay, anybody or everybody recite this. This is what?
Battery.
Okay. What's this?
Resistor.
This?
Capacitor.
What kind of?
Variable capacitor.
Okay. Variable. Okay. This one?
Capacitor.
Fixed capacitor.
Yeah. Okay. And this is? Transistor. It's actually a bipolar transistor compared to a field effect. I don't know why they make a big fuss about that. Okay. What this is, the circuit actually excites this thing, which is called a crystal. All right, it's a piece of quartz that's ground to a specific dimensions. So when it's shocked by electricity, it will vibrate at a certain frequency. Now I have this. Can everybody see this? I can't see myself.
I can.
Can everyone see this?
Yes.
Okay. This is, blast from the past, 1940s, 50s. And before we had, precision circuitry like we've had in the last, say, 30 or 40 years, we had to have a frequency standard. This is an oscillator. It uses a tube instead of a transistor. One is a power tube and the other one is actually the oscillator. And this thing is the crystal. The crystal is set for or ground to vibrate at a frequency of 100 kilohertz. Now, since we're using this to calibrate our transmitters and receivers and things of that sort, the circuit was made to generate a lot of harmonics. Anyone ever remember what a harmonic is? Aside from being a kid.
That's a harmonica.
Okay, harmonic is a multiple. No, just like you hit a key on a piano or strum a guitar, you're hearing not only the primary note, but you're also hearing multiples of that note. So what we're doing, we're generating 100 kilohertz. That's the primary frequency. Then the secondary harmonic, the second harmonic would be 200 kilohertz. And then 300, and this thing is good to about 30 megahertz. So it's very, very rich in harmonics. So what I have now, all right. I have my transceiver. It's set to 7 megahertz. And I'm going to turn the calibrator on and the audio. And you can see that it's, I have a signal at 7 megahertz. Now let's see. It's there at 7.1, 7.2, 7.3, 7.4, all the way up the spectrum. Okay, now that's very handy, but it also demonstrates something. You remember that we were talking about modulation last week and the week before. We were talking about taking a frequency, taking a signal, and then adding something to it, adding a voice to it. And what we're doing, we're combining two frequencies. I'm going to share screen again, and let's see if I can get. Okay. Okay. All right, this is going to come up. What we can do, and in the old days we had to do it because a lot of the equipment that we had just wasn't capable of covering high frequencies. So I have a receiver that will receive from 28 megahertz all the way up to, or to, say 32 megahertz.
Your gray screen, Jer.
I'm gray screen.
Yeah.
Move this window away from the shared application. Sorry about that.
There you go. We got it.
Okay, I want to get out of this one though. Okay, I'm going to get rid of this, and I'm going to open this thing. Okay, anyone see this?
We're still at your menu screen, or at your file.
Can you open it up and then share?
Right, I better stop sharing and start again. You're right. Okay.
Yeah, open it up first and then share.
Yeah, okay.
Does that computer have tubes in it?
Actually, my uncle was at MIT back in the 1950s, and they had a computer with tubes. They had kids walking around. It was the size of a football field. They had kids walking around with baskets of tubes, and every so many hours they would pull out one tube and put another one in to make sure everything was working fine. All right. Did this thing come up yet?
Yes.
All right. So, as I said, I have a transceiver or transmitter or receiver that will pick up 28 megahertz. I wanted to pick up 144 megahertz. Now, what can we do about that? We can make a crystal oscillator that operates at 116 megahertz. We have an antenna that's receiving signals at 144 megahertz. Put them in here, turn the switch, and a little paddle starts mixing the two frequencies together. Now, the problem with mixing is that it will combine two frequencies in two ways: a plus frequency and a minus frequency. 144 plus 116 equals 260. We don't need that. 144 minus 116 is 28 megahertz. And we can use that to go into the transceiver. And by tuning the transceiver from 28 to 32 megahertz, we're actually tuning from receiving signals from 144 to 148 megahertz. Everybody got that?
Yep, makes sense.
Yep.
Okay, great. All right. I'm going to stop sharing again, and let's see if I can. Okay. Does anyone see anything now?
Oh, you got to share again. Stop sharing, share again.
Okay. All right. In the same way, I can transmit from my transceiver at 28 megahertz, use pretty much the same kind of technology, an oscillator at 116, mix it, and it goes out to the antenna, and we have two signals that the mixer provides. One is 144 megahertz, which is our amateur 2-meter band. That's good. And it's also the difference, which is 88 megahertz. No, 28 plus 116 is 144. 116 minus 28 is 88 megahertz, which is right in the FM broadcast band, which we don't want to have any signals in there. So this one gets filtered out, but this one goes to the antenna. Okay, makes sense?
Yeah.
Okay. All right, I'm going to get out of this and start it again. Start share again, and all right, can anyone see this little box?
Yep.
Okay, and for a long time, people were buying transverters. Sometimes the manufacturing companies would make their own transverters, and for a little extra charge or a lot of extra charge, you can buy one, and plug one end of it into into your 28 megahertz radio, and plug the other into an antenna. Most of the time, people nowadays will buy two transceivers, one for HF and one that'll handle the two most popular VHF, UHF amateur bands, which are 2 meters and 70 centimeters. Anyone remember what the 70 centimeter band, what coverage that is? Okay, you got a chart at the end of chapter 1. If you have to look. Yeah, 1-23.
420 megahertz.
Yeah, 420 to, I think it's 450.
Okay.
Okay. Okay. All right, so that's mixing. And let's see if there's anything else we need to get into. Oh yeah, I wanted to show you the perfect transceiver that everyone really wants to buy.
Got to reshare. Yeah.
Okay. This is the new Kenwood TS99900 contesting transceiver. If you're in a 24-hour contest, you want to stay in your chair. So why not have a refrigerator, microwave, and coffee maker built in? Yeah. So
I'm on.
I want one of those.
You're sitting in the bathroom at the time?
pardon?
You're sitting in the bathroom at the time?
That you're going to have to arrange. I suppose a hospital supply would give you a special chair.
Oh my God.
Okay, but no, that's about it. But otherwise, no. Someone took a picture of a real Kenwood. I think it was a
Right.
9900, and which is a very bodacious transceiver. This I think is in the $3,000 class. They do have some that are in the $10,000 class. A little rich for my blood. Okay, that's pretty much it. So, any questions at this point? Nope. All right, let's turn it over to Bob then.
Okay.
Thank you, Bob, for the time.
Okay. Chapter 5. You know, there are lots and lots of little specialties you can get into with ham radio. Not all of them are going to interest you. Not all subjects in amateur radio are going to interest you. But tonight we're dealing with one that it just fascinates me. It's really the reason it's the reason I got into shortwave radio and then eventually into ham radio. Tonight we're going to talk about the subject of radio wave propagation. Years ago, when I was in the Army Reserve, back in the days when the reserve forces really had one big mission, and that was to fight the Soviet Union. In the late 70s through the 80s, when I was in the reserves, the Cold War was in full swing. And at that time, I purchased an AM/FM stereo with a cassette player. It used to be called a boombox. And this is a big one. And it's sometimes referred to as a shoulder model. And I used it as my entertainment center when I was living in an apartment. Well, lo and behold, this very analog set, in addition to two strips of frequencies that were AM and another one FM, there were two more strips of frequency labeled SW1 and SW2. Being a curious sort, I started playing around on those bands. They were the shortwave bands, and found lots of interesting things to hear. The most significant to me at the time was Radio Moscow. Yeah, I wanted to hear what the enemy was saying about us. Also prominent on the dial was Radio Havana. Yes, another commie station. Let's hear what they had to say. Yeah, but that wasn't all there was to it. There was also lots of other stuff on the radio back then on shortwave before the internet kind of started taking over. Many nations, all had these shortwave stations, to get their message out to the world for goodwill, and I'm sure also for propaganda purposes. And there was excellent programming from like Germany on Radio Deutsche Welle. There was a Swiss Radio International, of course, Canada, Radio Canada International. There was an HCBJ from Quito, Ecuador. You could dial in all the time. There was a Radio Exterior de España, All India Radio, just to name a few. I was really wowed that, with just this little radio and just a telescoping with antenna, I could pull in these signals from all over the world. I was just amazed. And I wondered how, then how that was possible when, my local FM stations sometimes have issues getting through, and my AM stations, you go through a tunnel and they're, blanking out. How does that happen? Well, a lot of these questions we will start to answer tonight's subject, radio wave propagation. Okay. Let's start. Let me get you a cool picture here. Okay, zoom. I'll see if I can do this right. Okay. Now, radio waves, they come through the air. Long distance radio waves come through the ionosphere, shorter come through the troposphere. And these are pictures read from your book. And the big things are, this ionosphere that we talk about, and different sources will give you different dimensions for the ionosphere. Our book tells us from 30 miles to 260 miles. You'll find other approximations. But still, it's in these layers where long distance stuff gets going. What happens up there is, as sunlight hits the ionosphere, it starts ionizing atoms up there. Up there, there are a couple of things going on. One is there's of course lots of oxygen, O2, and then of course there's the more numerous nitrogen, the N2 molecules. And when the sunlight hits them, the UV rays from the sunlight, they break up and formed ions. And more important than forming ions, it knocks loose free electrons. Okay, and this leads to all kinds of very, very cool things that can be done in the atmosphere. Now, let's talk about the different layers of the atmosphere. And I'm going to stop sharing this one and pull up another one that I like, that I think is a little easier to.
We have no pepperoni. I gotta go.
Quick question, and that is, if you considered a high orbit NASA satellite, where would it be?
High orbit, well, let's see. The ionosphere starts at where? About 30 miles or thereabouts?
30 miles, yeah.
And goes up somewhere around 300 miles. So I think your LEOs, low orbit satellites might be cruising through that. But you'll see they're not going to be very affected by the ionosphere.
Okay. All right. Can you see that?
Yes, okay.
Okay. Now, the different layers of the atmosphere, these are important, and there are some test questions on them. But the first concept to understand is the sky is different. The atmosphere is different day and night. During the day, let's see if I can make it a little bigger here. Okay. During the day, you've got 4 layers to the atmosphere. Actually, some people will say there's 5. Some people will say there's a sea layer. But anyhow, you've got this D layer, the closest to the Earth, and this D layer, it really has, for us, for technicians, it really has no effect. The D layer has really no effect on VHF. It has some effect on medium wave and some on medium frequencies and lower frequencies. The E layer The E layer can actually bounce some signals that are high frequency, not in the VHF range, but in the high frequency range, the shorter wave range, up to about 20 megahertz. But the F1 and the F2 layers, that's where you get longer bounce. The F1 layer can sometimes absorb some of the HF, but if you can get your high frequency, below 30 megahertz signal to bounce off the F2 layer, you can get some distance on that. Now that's during the day, but now during the night, something funny happens. During the night, the D layer pretty much, it goes away. The E layer shrinks a bit, and the F1, F2 layers, they combine. So these reflecting parts of the atmosphere, first off, they're higher up, and the density is somewhat different. Hang on, let me give you another very cool slide that I like. Hope I'm doing this right. Okay. Okay. This shows you graphically what's going on up there in the atmosphere. It's like you see on the daylight side, you see you've got all four levels, all four layers are in effect, but once the sun goes down, you see that this D layer is gone. This E layer becomes really, really lighter, and the F1 and F2, you see they combine into a single layer. So think about shooting a cue ball, and if you're shooting a cue ball and it bounces off here, it's going to come down at a smaller angle, whereas higher up, farther away, you can just get more distance. Oh, incidentally, this line here, you look where the difference between day and night, you'll hear about this referred to as the gray line, and that's where your propagation starts to change. Okay. Now, all this ionization that's going on, it's different at different parts of the year and at different parts and through different years. The ionization is affected by stuff ejected from the sun, and the more ionization, up to a point, the more ionization, the better. Okay, what affects the particles thrown out from the sun are the sunspot cycles. And sunspot cycles, they follow an 11-year cycle. That's the solar cycle. And at different parts of the 11-year cycle, you can have very, very low sunspots or very high sunspots. Let me show you. Sunspots have been tracked for a long time.
Oh, sunspots are good.
Sunspots are good, yes.
No sunspots are bad. And right now we're in a very bad part of the sunspot cycle, or hardly any.
Alas, yes. Here, let me make this a little larger. Okay. Now this is this is right out of Wikipedia, by the way. Anyhow, right now we are at the end of sunspot cycle or of solar cycle number 24, which is here. And if you compare this to cycle 22, you see that things used to be much better. This was back in 1990, and sunspot cycle or solar cycle 23 was not as good as 22, but it was still pretty good. But here, 24 has been awful. That's the bad news. Now, the good news is we are just about starting solar cycle number 25. And depending on who you read, Solar cycle 25 either begins at the end of 2019 or somewhere up through the end of 2020. Who knows? I don't. But anyhow, 25 is supposed to be not gangbusters, but at least a little better than 24. And the thing is, it's the way they count it. It starts off low. So right now you get your license. Your tech license will give you VHF privileges, which is basically, local communications, which is great. But you go on and get your general license that gets you the HF frequencies, the 3 megahertz through 30 megahertz. You do that in a year or two, and you'll notice the sunspots will be becoming greater frequency. So for the next several years, we can expect to see the solar cycle cooperate with us and get better. This little graph on top, it just shows, they've been tracking this since the mid-1600s. And it's not as bad as it was. There was this Maunder minimum. I just thought that was interesting. That period coincided with what was called the Little Ice Age, although it's not clear that it had anything to do with it. Okay.
Very bad radio reception back in the 1600s.
Since there was no radios.
Right. Okay. Bob, can I contribute a little something?
Yeah, I'll stop sharing.
Okay. Well, all right. Okay. Number one, the 10 meter band where you have voice privileges as a technician. Right now, the ionosphere does not support any of the layers of the ionosphere does not support long distance communication to any extent. Every once in a while, there might be a little stirring. So you can talk about 10 meters as pretty much the same as 2 meters, so line of sight. If your antenna can see the other antenna, then you can contact them. The other thing is that not only do the radio waves bounce off the ionosphere, but they will bounce against the Earth, especially the ocean or thereabouts, and then bounce back to the ionosphere. So you might get one or two skips to get you around to the other side of the Earth. So you can get some very good long distance contacts there. Okay, Bob.
Okay.
So is nighttime more desirable for long distance communications than daytime? Is that what that was saying?
Not really. Certain bands, like 20 meters, 14 megahertz, and 15 meters and such, are most active during the day. 20 meters is one that almost all the hams try for long distance communications. At night, it changes when those layers kind of collapse. At night, the lower bands, like 80 meters, 3.5 to 4, and 40 meters, 7 to 7.3 megahertz, they come into their own, and you get some long distance skip. I talked to a couple of guys in France and Russia and Bulgaria on 7 megahertz at night with the wire antenna. It came out just fine. And at that point, I couldn't hear anything on 14 megahertz. The radio waves just went straight through, and I guess the guys in Alpha Centauri are listening to us.
So the signal is better. There's just less people.
No, not that. It doesn't have anything to do with people. It's the way that the your signal bounces. It either bounces off the ionosphere and is reflected back to Earth to someone else to listen to you, or it'll go straight through the ionosphere and not get bounced back at all.
Okay, that makes sense now.
All right, Bob.
Okay. Yeah, and here's kind of the graphic of what Jerry was talking about, is that, Ryan, so for your question is, it depends what frequency you're on. So, yeah, because those lower frequencies during night, yeah, you can do fine. But you get to higher frequencies and no, night's not necessarily going to be your friend. For frequencies in general, you know, the lower frequencies, the HF frequencies, they do bounce off the atmosphere like that. But as the frequencies increase, if the frequency is too low, it doesn't bounce off the atmosphere. It just gets absorbed and doesn't go anywhere. But when the frequency starts getting too high, then it does not bounce off the atmosphere, it goes through. Now, that's not necessarily a bad thing. Think about if you want to bounce your radio signal off the moon. And a lot of guys do that for fun. It takes some talent, takes some equipment, but you want a radio signal that's going to go through the atmosphere. What if you want to communicate with the International Space Station? Same thing. You need a signal that's going to go through the atmosphere and not bounce off. So, for instance, it's very common I know for the International Space Station, for most satellites, it's very common to have an uplink frequency and a downlink frequency. The uplink frequency usually is in VHF land, which is what your tech license gives you privilege. Okay, so you uplink with, you transmit to the satellite with VHF, and the satellite transmits back to you on UHF, which is going to be in the 430, 440 megahertz range, which also you have, as a technician, you will have access to. Okay. Yeah, but, and again, the solar cycle, it does matter. For the 10-meter band at, right now, it's brutal. It's the 10-meter band is not so good, but at a solar cycle maximum, a 10-meter with 10 meters, you can usually make long distance contacts from dawn to sunset. Dawn to sunset, not at night. And in fact, at solar max, even the 6-meter band can refract somewhat. It will refract on the F layer. There's another thing, okay, so these are two big ways. One is direct and reflecting off the atmosphere. Well, you know what? I have a better, let me get a better graphic for this. This one. And I would, I think, let's see. For this one, I would like to thank the United States Navy for this. It's out of one of their training manuals. Okay. This shows you, the different ways you can communicate. One is simply plain old ground wave, I'm down in the lower right-hand corner where you're simply communicating right eye level. Then there's sky level or sky wave where you're bouncing it off the atmosphere. Jerry talked about multiple reflections where you bounce it off the atmosphere once, it comes back down, hits the earth, bounces off again, reflects off the atmosphere a second time. It can do that multiple hops and you get quite a distance. All right, and then there's this E and F layer. And this isn't the one, well, this will do, I guess. There's this thing called I thought I had a specific tropospheric ducting.
I have a map if you want to let me put it on.
Okay, here, let me stop sharing. Okay, go ahead.
Okay, has this thing come up yet?
It's on the way. There we go.
Okay. Tropospheric ducting is a case where usually it's in the tropical areas or southern areas where you have a layer of warm air on top of a layer of cold air. And somehow or other that takes radio waves and bounces them. And this is a map. Let's see, I don't know if I have a legend. Yeah. You can see zero to fair all the way up to very intense. And this map is showing areas where it's pretty intense. And if someone is in, two people are in this area, within this area, they can talk to each other. There have been times when a fellow in Michigan was sitting in his garage with his 2-meter handy talkie, talking to some guy up here. So it can be done. So that's something to look for 2 meters and also 6 meters. Okay, back to you.
Okay. Let me see.
So do we have to become weathermen in order to determine our signal strength?
I will send you the link. There's also something else that's I'm sure Bob will probably talk about later. But they have these websites where they send spotting messages, where someone's on a certain frequency and they talk to a long distance station and they want to brag. So let's say I just talked to a guy in Peru on such and such frequency. Then everyone sees his brag, and then they say, "I'm going to get him too."
Yeah, there's lots of information about it. In fact, the ham radio magazines, this one, for instance, CQ Ham Radio, every month has a, can you see it? It has a regular article on propagation and what you can expect for the month ahead. The ARRL magazine, while it doesn't have a specific monthly column about propagation, it frequently has articles about propagation. In this case, this is one about weak signal propagation reception. And yes, and then there are the websites that will tell you the same thing. Okay, let's go back to this one. Okay, so we talked about, we're talking about line of sight for a VHF. Actually, you'll get a little more distance than actual line of sight. The direction is line of sight. You're not bouncing off the atmosphere or anything, but the radio wave does tend to follow the curvature of the Earth a little. So actually, your radio wave can go further than you can see. Okay, that's one. There's also, on occasion, something called tropospheric or sporadic E, which is kind of just an opening for probably due to ionization in the E layer, where all of a sudden you can just get a lot of additional distance on 2 meters, 6 meters, and 10 meters. This tropospheric ducting that Jerry was talking about, this is the slide I wanted to show you about that. When warm air, traps a layer of cold air beneath it, what happens is, say that this black line here, do I have a, this doesn't give me a, oh, no, damn it. Undo. Well, I don't know how that worked. Okay, let's go back here. Okay, in the normal line of sight where, you know, you have your radio signal, it goes out here, you get this far, the rest of your signal goes right out into space and no one hears it. When this particular air inversion happens, what happens is your signal can actually bounce off this duct, you know, this tropospheric ducting. It's like the weather pattern forms a tube almost, where your signal can go through. It bounces off the limit of it and then reflects as though it's reflecting off the atmosphere. You're not up in the ionosphere here. You're in the troposphere, but you're still getting some additional distance by your radio signal reflecting. There's a couple other things, and Jerry gave me these couple of really cool files that, you know what, they're not visual, they're sound files. You know, if you read the chapter, you read about how your signals, there's two other things. There's the aurora borealis, that ionization of the atmosphere that happens toward the north and south poles, where your radio signal can actually bounce off that ionization. Now, oh, get out of here. Hang on, I'll be right with you. There is. Oh, here we go.
5 and 8 Aurora, 5 and 8 Aurora, Fox November 3-2. Oh, Charlie 2, Whiskey Lima, Radio Aurora. US Nice to see you again. That beautiful signal on the Aurora. 9 Aurora, you're 59 Aurora, Fox Starway 25, over. QSL Kevin, you're also 59, 7-3, thank you.
Yeah, and the signals don't seem to be coming from any specific direction. That's when things hit that aurora borealis.
Yeah, it sounded, yeah, but you heard the distortion of one of those guys. The clear one you heard, I forget his call sign, Victor Echo something. It sounded like a Canadian station. I don't know who the other station was. I was going to look it up and I forgot. Jerry, do you remember? It was a distant station anyway.
Right.
But anyhow, that's bouncing a radio signal off the aurora, which is just cool. I mean, it's beyond my skill, but it's above my pay grade, but it's still just cool. And for those of you who wish to pursue that, it'd be a heck of a goal and a heck of a plum for you to get that. You can also, you know, there are hundreds of meteors that streak through our atmosphere, you know, every day, and they leave ionized trails, and you can also bounce signals off that. Again, you got to be pretty good, I guess. Again, this is above my pay grade. The ionization only lasts seconds, you know, and it's mostly stuff going on in the E layer. But let me play you a meteor scatter.
You have to make a tape recording of that and play it over 100 times to figure out what they're saying. I think nowadays people are using digital techniques which give all the data all at once, so they can I'll figure it out there. We'll get into digital later.
Okay. All right, but that's what meteor scatter sounds like, and very cool. I don't think it's easy to do, but
Hey, Bob, there's a test question about that. So the media scatters on the E layer. Is that what?
yes,
Okay, there's a test question on that.
yeah. Essentially, it's going to be on the E layer. Okay. Now, let's talk a little bit about screen share. All right, we'll go back to talking. We're talking about bouncing signals and whatnot. You know, when you're bouncing signals out there, lots of things can happen. You know, you bounce your signal, that's called reflection. There is refraction, another way of saying, and that's just refraction is when your signal is bent and turns up. Diffraction, we have a slide later on. When I get into the formal part of the to the ARRL slides, there's a nice graphic. There's a nice graphic on knife edge diffraction. And essentially what that is for those signals that are traveling direct path or line of sight, they can be affected by running into buildings, you know, either stopped or bounced. Dispersion, you've got to remember the concept of dispersion is that as your signal gets further away from you, the power is dropping. All right. Absorption, you know, for some frequencies, your signals can be absorbed by plant life and vegetation. So, you know, if you're in a forest and working on the wrong frequency, you know, you could have a distinct loss of signal due to stuff being absorbed by the trees and bushes and whatnot.
Some frequency, even rain will start absorbing.
Yeah. There's another concept that the book talked about and that's important to know about, and that is multipath. You know, your signal goes out and it's going out in all directions. This graphic is, you know, just shows, oh, well, of course, this graphic is showing as though it's using a directional antenna. Even with a directional antenna, what can happen is, you know, part of your signal can travel, you know, depending on how far you're broadcasting, part of your signal can travel, you know, ground wave, and another part reflect off the atmosphere, and that your signal can get, your signal in two flavors can get to the recipient at slightly different times, or even at slightly different phases, or polarizations. So, and that can, wow, depending on your luck, that can either wipe out your signal, degrade your signal, or maybe not. All right.
Well, flutter your signal too.
Flutter, I'm sorry. Yes, yes. Well, think about it. Think about if you're traveling in a car and you're using, like for instance, 2 meters. That's essentially line of sight, and you're driving through a city. Well, some of your signal may get through unless there's a building next to you. Then you're driving down the street, and then you're in free space, and then you come across another building, and your signal is going in and out and in and out. Something referred to as picket fencing. Okay, we talked about tropospheric already. Oh, you know what? Let's stop here and let us pick up. Just to make sure we're getting all the. Wait a minute. Hang on, Jerry, I'll be right there. Okay. Now, let's see if I can. Okay. Okay. This is the formal part of the presentation, and I just want to make sure that we got all the nomenclature here. We talked about line of sight. We talked about ground wave. We talked about sky wave. Line of sight, yeah, also called direct path. We talked about that.
Okay, we can talk about poor Hugh and where he is right now, which you're about what, three hours north of where we are?
Right about that, yeah.
Okay, and unfortunately, he can have as good an antenna as possible, but he can't hit our repeater because he's out of sight. His radio waves are bouncing against the curvature of the Earth.
Well, Jerry, can't we put that on a weather balloon to get it up a little higher?
I should say, yeah, about 30,000 feet.
Oh, okay.
So where is Hugh that he's out of sight? He's up in Midland, or?
I'm just east. I'm sorry. I'm just west of Hale, and I'm south of West Branch.
Ah, okay, that's where you are. Okay, got it.
33 and 55, just south of there.
Okay. All right. Ground wave. We've talked about the HF frequencies can follow the Earth's surface a bit. The waves can travel beyond line of sight. Yes, we've talked about that. It follows the curvature of the Earth. It's the radio horizon, is sometimes referred to as the radio horizon instead of just your visual horizon. Range of a few hundred miles on amateur bands. We've talked about refraction. Okay, here's the graphic I was talking about. This diffraction, so the radio source hits this sharp edge of the building, and what happens is your signal becomes broken up, and there are parts past that building where people are not going to hear anything. You see in the white zones, and there are parts in there where people are going to hear your signal, maybe a little distorted, maybe a little weak, but they'll hear it. But there's lots of areas where, yeah, they're not going to hear anything. Okay. Oh yeah, buildings can block line of sight, but they can. But the buildings, the sides of the buildings can also reflect your signals, and you can bounce your signal off as, you know, like a cue ball or like a pool ball, bouncing around a pool table. Multipath. Oh, we talked about multipath and picket fencing. Tropospheric, yes. The troposphere, yes, begins about 30 miles high. Radio waves can be scattered by clouds, yes. And densities, troposphere range up to 300 miles, depending on who you ask. One of the sources I looked at was from Radio Society of Great Britain, and they, of course, they did everything in kilometers rather than in miles, but they set the height of the troposphere at 625 kilometers.
Oh.
which would be about 400 miles. Okay, temperature inversions. Yeah, we just talked about temperature inversions. Yes, we talked about the ionosphere.
Okay, we didn't talk about skip that much, or a skip zone.
Okay,
That's kind of important in the high frequency area. Right, a friend of mine, Bill Bonds, lives about 15 miles away, or lived about 15 miles away. He's silent key now, but he put a new antenna up, and I said, well, why don't we try it out? So we made arrangements to he'd transmit and I'd listen. No, we try to have a conversation on various bands, and no, it was fine on some bands. Other bands I couldn't hear him at all until some fellow came up and told me, you can't hear him, but I can hear him fine. His signal was actually skipping over me and bouncing off the ionosphere, but I couldn't hear him. So that happens. That happens quite a bit.
Yeah, unfortunately, in that skip zone, it's not like everyone gets showered with the radio signals. It's the radio signal bounces over you, so you can get some distance, but you can get distance, but it's not continuous distance.
Right. Okay, and one other thing, you were talking about polarization a little bit. Do you have anything on that, Bob?
Yeah, that comes up later.
Okay.
We talk about antennas.
Okay.
Okay. And the sunspot cycle, I think we beat that to death already.
Oh, I wish we could pump some life into it.
Yeah, I know. Okay. And skywave or skip, yeah, responsible for most over the horizon. On HF, skip is very rare on 2 meters and on higher bands. And ground to sky is called hop. And I think we've covered that. Okay. All right. Highly ionized patches. The E layer can reflect HF and VHF. Okay, we've talked about the 10, 2, and 6 meters. We talked about the aurora. And meteor scatter, yes. Okay, that's that. I do like that subject. I really, really do.
Well, you're going to have to buy yourself a place with about 40 acres so you can put up all those beautiful antennas.
Oh, indeed. Yes, indeed. But what am I doing? That's not what I want. Hang on.
By the way, this is one of the more funner classes.
Well, glad you're enjoying it.
Agree.
Okay, let's see if we can do this. See if I can. Okay. The thing is, this is just, tonight we just have cool subjects. That's all. And I hate to tell you this, but next week is going to be even cooler. Next week is chapter 5, and it's parts. Parts is parts. But after that, chapter 6, 7, 8, and 9, they're not going to be fun. You're going to need to know them, and we'll try and make it as painless as possible, but it's more administrative kinds of stuff that you need to know for the exam. So, I hope you enjoyed last week. I hope you enjoyed tonight. And I hope you enjoy next week. I won't be here next week, but I hope you enjoy next week. But,
next week.
Those last 3 those last 3 are they're just work. But we'll try and make it as painless as possible, and it's easier material. Okay. All right, let's talk a little bit about antennas. All right. Now, the whole point about the antenna, you know, we talked about this really a little bit last week and the week before, is what the antenna, it's going to throw out your signal. It's going to take your radio signal from your transceiver and turn it into a radio wave. A radio wave, which is, yes, an electromagnetic wave. We'll talk a little bit about feed lines and little matching equipment, whatever. Elements. Okay, elements. I don't know why they introduced this right at this point, but they do. An element. And let me, you know what? Let me stop sharing this. And let me show you something. Let me show you. Gary, why are you on? Okay. All right. Let me show you, as we talk about that. Can you all see this?
Yes.
Yeah, what
Clothesline.
That is one cool antenna.
yeah.
Is a superb antenna. Anyhow, so we're talking about elements. Okay. Credit where credit is due here. This is my 2-meter Yagi antenna built by the illustrious Hugh, K-E-A-T-E-D. Thank you, Hugh.
All right.
But anyhow, so we're talking about elements, all right? These are the elements they're talking about, is these.
Yeah, well, a beam antenna is sort of like a magnifying glass. Yeah, a magnifying glass. You know, when some of us were wicked little boys, we'd take a magnifying glass out and set fire to grass and things of that sort, because we'd be able to take the energy of the sun and concentrate it into a beam of very intense light. The beam antenna, it does about the same kind of thing. Doesn't it, Bob?
Yeah, exactly. Now, I don't know why they make a big deal about parasitic elements, but those are elements that are not connected to the electricity, like this one. On this antenna, this element is the driven element. You'll see, if I can show you right here, this is where the coax cable connects right up here and goes and feeds this particular element, okay? And then these up here are director elements. Back here, this is a reflector element. No big deal. And of course, this long piece is referred to as the beam. Ignore this streamer here. Ignore that. That's not part of the antenna.
Yeah, long piece is a boom.
No.
Clancy lowers the boom.
No, you know what the streamer is for? It's like, since I live in a condo, I can't put up an outdoor antenna on a permanent basis. So when I want to play radio, I have to run outside. I have this nice tripod with telescoping pieces, and I can get this antenna about 30 feet up in the air. But think about Sunday night, and it's usually like this. But but think about Sunday night, 9 o'clock, when we have the net, and I am sometimes net controller for the net. Well, it's dark out, and when I get this 30 feet up in the air, remember, this is a directional antenna, and I have to point it in the right direction. And 30 feet up in the air, I need to know which end is forward.
Which is reflect.
Yeah, because you need to point it in the right direction. So that's what that's for, because down on the ground, here I can tell, but when it's up in the air and it's dark out, I can't. So anyhow, this is your beam. These are your elements. This is the driven element. That's a reflector. Okay, and reflector element.
Yeah, the reflector is a little longer than the driven element, and the directors are a little shorter. And I have a beam antenna for 2 meters. I'm not bragging. It's just, when I put the tower up, I wanted to have something good. And it has 10 elements.
Oh,
What, and well, it's cost less than $150.
Wow. I wish I could have got away with that.
Well, you can get a bunch of scrap metal and a piece of wood and make your own beam.
Don't get me wrong, Jerry. I got right now, working 11 meters. I got a 40-footer back there right now. That's 8 element. Because when Bob held that one up, I said, yeah, small version of what I have, in the house version of what I have, But like I said, 40 feet, and I'm sitting on top of 55 feet of tower. So I mean, the concept that you guys are talking about here, yeah, I understand that clearly when you say directional and what have you. I mean, one thing about that, I mean, anybody get into it, and I mean, it'll excite them because you never know where you're going to point that, which way you're going to point that antenna, and who you're going to hear. And I found out that it's a whole new ball game. Yeah, I mean, even local. I mean, don't get me wrong. Every now and again, you might squeeze that short skip, but yeah, like I said, it's interesting. I'll put it that way. Hopefully everybody else will look at it the same way I look at it. It's interesting.
Yeah. Well, you don't need a beam antenna to make contacts. That's for sure.
Yeah, exactly. I mean, you could do it ground plane. I mean, as a matter of fact, I got a friend of mine now that he just got his tech, and he's working the dipole and what have you. And I was over there one day, and he was showing me. I mean, it's amazing. I'm saying to myself, I said, "Oh, you could do all this on a piece of wire?" And he says, "Yes, it's possible." So I mean,
Sure.
That's my move.
okay. All right. So we're talking about the radio waves, and the radio wave is made up of 2 specific waves. One is an electrical field, and the other is a magnetic field. And these things travel at 90 degrees to each other. Now, it can make a difference which way the field is pointing, right? This is referred to as polarization. Now, polarization is always defined by the electrical field. So in this case, where the electrical field is blue, and that's the blue line, the blue sine wave, all right? This is vertical. Let me make this a little bigger. Oh no, on this one I can't make it bigger because it's a motion thing. Anyhow, because the blue wave here is perpendicular to the Earth, this is vertical polarization, and the red sine wave, that's the magnetic field. That's horizontal, but it's vertical polarization because you define polarization by the direction of the electrical field. Now, on 2 meters, if you're doing regular 2 meter FM, the polarization is usually vertical. Jared, do you want me to stop sharing?
No, I'm just holding up a handy talkie with a vertical, antenna, and the polarization is vertical.
Right. Now, if the antenna were pointed horizontal to the Earth, that would be horizontal. Yeah, that would be horizontal polarization. Now, for most 2 meter and UHF also communication, for FM, it's normally vertical polarization. Now, for some reason, the ARRL finds it important, or maybe it's the FCC finds it important, to put a question in that can appear on your tech test that says, what's the polarization for 2 meters for single sideband? All right, now that's not FM, that's single sideband when you're getting distance. In that case, it's horizontal polarization. Okay, that question can appear on your exam.
I think, do they have anything?
Yeah.
Go ahead, Victor.
Oh, no, no comment.
Well, that's Mike. I said I've seen that question multiple times.
Yeah.
Okay, now here's something that we do talk about, vertical versus horizontal polarization. If I have a horizontal antenna and I'm doing FM on it, the difference, there's a signal loss, a very great signal loss. I think it's about 18 decibels, which is, yeah, I don't know, I'm not a math whiz, but you lose a lot of signal if you're transmitting horizontally into a vertically oriented receiver. I'm not sure whether there's a question in that for that or not, but no, it's just a practical thing.
I got a question, Jared. Now, if that's just okay, you're saying you lose a lot of the signal if it's just stationary, or if you're able to direct that signal, what's the plus and minus side of that?
Okay, well, 18 dBs. If you use any kind of a beam antenna that's horizontally polarized, you can get, well, for 2 meters or thereabouts, you can probably get about 8 or 9 decibels gain.
Okay.
And you put that against 18 decibels gain loss, and there you go. All right, Bob has just put up a beam antenna radiation pattern.
Yeah, Jerry, while we're talking, this is a great time to talk about gain. I was kind of hoping that there's a slideshow resize. I was kind of hoping there was a tool here where I could do a little thing. At any rate, here's the deal. Victor, you're talking about if you've got just a vertical antenna, a plain vertical antenna, your radiation pattern is going to look like this dashed circle right here.
Omnidirectional.
Omnidirectional, yep. It's going to look like that dash signal. If you go with a beam antenna, a directional antenna, most of your power is going this way. On your omnidirectional vertical antenna, your power, remember your power decreases as you get further and further from your site, from your transmission site.
Right.
So with an omnidirectional, half stop that. half of your power is going in it. Say you want to make a contact in this direction as far out as you can, but with an omnidirectional antenna, half of your antenna power, half of your transmit power is going in a direction you don't care about.
Right.
Whereas your directional antenna, look, half of your power goes in this little arc, this little part of the circle. Now, to kind of compare, think about this. All right, you've got your beam antenna and you're getting out this far. All right, now what's happening if you go to your vertical antenna? You go to your vertical omnidirectional antenna, all of a sudden you're not getting out this far. All of a sudden you're losing, 7 or 8 decibels of power. And that's a lot.
It's as if you cut your power by a quarter or by 75%.
And while we're here, let's talk just a quick second about decibels. Decibels. Oh, I know. Jerry, you know what? Decibels are, it's a logarithmic function. You know what? Now, I was really good at logarithms when I was a junior in high school in 1965. That was 55 years ago. I don't remember logarithms that well. But for your tech exam, listen to this. I want you to remember 3 numbers, all right? Number 3, -6, and 10, positive 10. Positive 3, -6, positive 10. If you go in your book, go back to page 1133. And look at questions. Look at questions T5B09, 10, and 11. Okay, now I want you to remember those 3 numbers, 3, -6, and 10. Okay, now this first question, what is the approximate amount of change measured in decibels of a power increase from 5 watts to 10 watts? Now I want you to look at those potential answers, and I want you to remember 3, -6, and 10. Okay? This is the only difficult one, because if you look at the possible answers, you see that there is 3, but there's also 10. The correct answer here is 3. And you say, well, you're going from 5 watts to 10 watts. Well, it sounds like it's doubling. Yeah, but no, it's a logarithm. If you do the logarithmic calculation, it turns out to 3. So the answer to this is 3. If you look at the next question, what's the approximate amount of change measured in decibels of a power decrease from 12 to 3 watts? Now remember those 3 numbers I told you to remember. 3, -6, or 10. Do you see any of them in those answers? Yes, you do. You see -6. That's the answer. And the next question, what is the amount of change measured in decibels of a power increase from 20 watts to 200 watts? Again, think about those 3 numbers I told you. 3, -6, or 10. What do you see here? The only one you see is 10, so that's the number. All right? So, you know, if you're really ambitious and really, really good with math and want to figure out the logarithms for decibels, oh, bless you, bless you, bless you. If you don't, remember 3 numbers, 3, -6, and 10, because you're only going to get 1 decibel question, and one of those numbers is going to be the answer. And if you just remember that a power increase from 5 watts to 10 watts is a 3 decibel gain, okay, you're golden. Okay, now, the one other reason I wanted to switch to this is, and Victor, this is for you specifically, you know, because you were talking about, you know, what kind of loss do you get, and in this case, you see from an omnidirectional vertical antenna, from a directional beam antenna, a directional antenna, you're losing 7 decibels, about 7 or 8 decibels. Now look at this question 10. A power decrease from 12 watts to 3 watts is -6 dB. So if you look, and here you're losing 7, you're losing 7 dB or 8 dB. You have a power drop of more than, well, in this case, it was, what's that, 2/3. That's a big deal. That's a very big deal.
Okay.
Hey, would you ever want to use an omnidirectional, like say I'm out hunting in a large farm field, like hundreds of acres? Would I still get reception in this omnidirectional?
Oh, sure.
Well, how large a field and what frequency, and you're talking about a handy talkie?
Well, yeah, it'll be ham radio. I mean, or amateur radio, like in the 2 meter or the.
Okay, you have a handy talkie. That's good. And how large an area? Because these things.
300 acres with tree lines.
Okay, so what's the maximum distance between one point and another in that 300 acres?
I don't know. I don't know what the blinds are set up at.
Okay, well, I mean, these things are good for about 1.5 miles. You can extend it a little bit by getting an off. We talked about an off-market antenna. That's yeah. This would increase the effective power by about 1.5. There was a friend of mine who was trying to do things with his emergency management group, and he found that an aftermarket antenna did increase the range from 1.5 miles to about 3 miles.
Okay.
So you can try that, although that's really stretching it.
Again, you got to think if there's a change in height or change in elevation between you and your target party. If they're below you, that could affect you positively. If there's lots of vegetation, well, that may degrade it a little bit. But
well, if the blind is up in a tree, you might have a little advantage there.
Oh, right.
Little height there.
Okay. Okay, and we talk about gain. All right, this is a concept you just should understand. Is what they're talking about in gain is just gain is always a relative term. So it's relative to what you would get with an omnidirectional antenna, meaning this dashed line circle. What does your special directional antenna, how much more power do you get in the direction you want to get it? Okay, because you see, let's say the top here is north. In the southerly direction, you're getting very little. So, you got to decrease. But in the northerly direction, if that's where you want to go, with a directional antenna, you have gain over what you would get with an omnidirectional antenna. Okay, so for instance, I think it's safe to say there's no such thing as gain with an omnidirectional antenna.
Well,
I know it's not quite right because it's gain relative to an isotropic.
Yeah, it really isotropic is an artificial concept. It's a point in Never Never Land where the radio signal emanates. We used to measure it to a dipole and compare it to a dipole antenna, which is a real antenna. The isotropic radiator is, 2.1 dBs less than a dipole?
That sounds about right, yeah.
Yeah, okay, so I think the antenna manufacturers love it because we're that much more gain over an isotropic, where it's if you had to compare it to a real antenna, dipole antenna, it's not as much. It's almost like the proof for whiskey. A 90 proof whiskey is actually what, 45% alcohol?
Yes, right. Which is still pretty wonderful.
Yeah.
Okay.
quick question. Do they have handheld directional antennas?
Yes.
Oh, they do? Do you get
Yes.
more, do you get too much radiation from those, or RF, I mean?
No.
Not at 5 watts or thereabouts. No.
Okay.
Actually, what you could probably use is one of those satellite tracking antennas. That would give you some gain, and they're handheld.
Yeah. Do you know? Yeah. You know, handheld. Are you familiar with the term fox hunting?
Yeah, I was reading about that directional radio finding.
Directional radio finding. Yeah, that people play games with that where they hide a small transmitter and then people try to find it. Well, to do that, they use handheld directional antennas. They look like small Yagis. And I haven't done that, but I know people who have it, I suppose, and I hear it's supposed to be a blast. But so yes,
there's a professor in there's a professor in Ann Arbor who used to hide his hidden transmitter in places where no one would suspect, and just turn it on for a couple of seconds, and drove the guys crazy, but gave him a really nice challenge.
Okay, when I get ready for his lessons, I always worry that I'm not going to have enough to say. But you know what? It's like it's 20 to 9. We're running out of time. Let me move on to talk about standing wave ratio and SWR meters. For those of you here, by the way, is an SWR meter. This is the standing wave ratio is a concept, an important concept. When you key your microphone and you try to send out a signal, if there's not a good match in impedance between your feed line and your antenna, some of that signal you're trying to send out is going to come back to you. It's not going to go out your antenna. It's not going to be radiating out into the atmosphere. No, it's going to be coming back. And instead of that power being diminished by sending it out as a radio wave, it's going to be diminished by heating your feed line. Now, that's a big deal. If this ratio of forward power, the power going out the antenna, to reflected power, the power coming back to the transmitter, if that gets too high, bad things happen. Now, nowadays, most radios have built-in protection, and what it will do is it will start reducing your power, automatically reducing your power to prevent too much power coming back and blowing out your circuits. But anyhow, the way you measure that is with one of these cool little meters. Now, these are not expensive devices, and they're the kind of devices that they're fairly simple. So, you can have some confidence buying used equipment. I bought this one used a while ago. Real simple devices. On the back, there's only 2 connections. There's one connection that goes to your transmitter and one that goes to your antenna. And what this does, it's called a tuner, but it's not really tuning your antenna. All it's doing is matching the impedance. Okay, so your transmitter is expecting, 50 ohms of impedance. And if you're getting more of that coming back from your feed line, this will take care of that. Now, it's kind of interesting. There is one test question I want you to be aware of. There is one test question that asks, what other implement or what other instrument besides an SWR meter can you use to measure SWR? And what that is a directional watt meter. Now, this particular SWR meter can also be used as a watt meter. There's a selector switch up here that switches it from SWR to a watt meter measuring forward watts forward power, and then reverse power. So if it's measuring forward power and reverse power, that's what your directional watt meter does. And that can also be used. And again, like I say, I don't know anyone that specifically uses a directional watt meter, but there's a test question on it. And so I want you to know that. Okay. Now, let's talk just a few minutes about what causes high standing wave ratio. And probably, if you're using a dipole antenna, probably the most common thing is an antenna of the wrong length. A second would, because the antenna length has to be related to, in some way, either a full wavelength, a half wavelength, a quarter wavelength, has to be related to the wavelength you're trying to receive or trying to send out. Okay, what else is if there's something wrong in your feed line, a faulty feed line. We haven't talked about feed lines much. We will later. It's really kind of a simple subject. The feed line is simply your coaxial cable, right? Cool thing. This coaxial cables can be either very small or very large, depending on what frequency you want to be using it on, how you want to install it, and how much money you want to spend. The RG, this is RG58, I believe.
Yeah.
It's really easy to work with. It's not very expensive. I think it's, I don't know, 20 cents a foot or something like that, maybe less. This is LMR 400. It's much thicker. It is much lower loss. But you know what? Where RG58 is very, very flexible, this is not so flexible. Look, it's got a great big dielectric in there. So it's harder to use, but if you're working up in the high VHF or UHF areas and you have to have a long feed line, you may need to go to this.
And also, it'll take a lot more power than the RG58.
Okay. Well, for those of us who don't have linear amplifiers, it's
Right.
an interesting point. I have not yet dropped that $3,000 on a linear amplifier.
Right. Well, you can buy all sorts of stuff at swaps.
Okay. Okay, what else? Oh, the other thing, another common one for high SWR is a faulty feed line connectors. These things they connect with usually with screw-on connectors. And if you don't have it, all the way set, or if you've got water in the line or something, that can degrade your transmission and force up your standing wave ratio. Okay. I think I had a slide on that. In fact, was that a particularly good one? Yes. Oh yeah, I showed that one. The only interesting thing about that is okay. The only thing to remember about this is that there is one test question that asks you, where do you connect your SWR meter or your watt meter? And that is, it's connected between your transceiver and your antenna. Okay, the antenna comes in and you connect it right there. I'm not sure that's obvious, but but now you know. Okay. Okay. What do we got to go on? Oh, Dipole antennas. Oh, practical antennas. Let's look at that. Okay, the dipole antenna. We'll get to a good graphic on this in a little bit, but for right now, the dipole, in fact, do I have one readily available? And dipole photos. I don't need that anymore. Don't need that anymore. I don't need that anymore. Huh. No, I guess I don't. I thought I did. Oh, maybe there's one in here. Okay, the dipole. The standard dipole, and again, this is not as, by the way, am I screen sharing?
Yes.
Okay. Okay. Okay, the standard dipole, normally half wavelength. So you don't normally use a dipole necessarily on VHF. A dipole for VHF, well, it'd only be a total of about 6 feet long. But for instance, on 10 meters, you may well do that.
16 feet for 10 meters.
Yeah. Okay, so you'd have 2 equal halves strung out, held on each side by a nice insulator, and with a feed line connecting in the middle. Now, this is something Jerry tells me. The egghead formula says you can estimate the length that you need in feet by taking 468 and divide it by the frequency. But Jerry says that's probably not a good place to start. You may want to start more like 490 divided by the frequency, because you get a little longer.
Yeah, it's a lot easier to cut than to try to stretch a wire after you cut it.
Yeah,
what do they say? Measure twice, cut once.
Yes. Okay. Okay, now this is the radiation pattern of a dipole. This top view is looking down on it, okay, as though you're looking down from the heavens. And this shows that the dipole, the wire runs this way, runs horizontally, and your field of transmit and receive runs off the sides, not the ends. It runs off the sides. This other, the 3D radiation pattern just shows you, like, if your dipole is elevated up in the air, well, what happens to all of the power? And you notice it's shaped. The radiation pattern is shaped like a bagel. Okay. Now the ground plane antenna, and this is something Victor mentioned before. Oh, here's the basic look of a dipole. You've got a center connector, a center insulator, an insulator in the center, a half of a wavelength, and you spread it out and hook it to another insulator and support it. And same with the other side. And you connect the feed line part of your coaxial cable goes to one element, and usually it's your braid from the coax you hook up to the other. So, okay, so that's the dipole. Your ground plane antenna, this is normally going to be a quarter wavelength or sometimes 5/8 of a wavelength of a vertical type antenna. And then it will have a conductive ground metal. Now, you can see this can be like a magnetic antenna that you stick in the center of your car roof, and your car roof acts as this ground plane. Or if you're doing this in free space, if you're just putting this up on a tripod or something, you would have these radiator elements, radials, that would either be, I've seen them both flat and I've seen them angled downward, and they act as your ground plane. What the ground plane does, in effect, it's like a reflection of the vertical part. So your vertical part is only usually a quarter wavelength, and so your ground plane, what it does is it acts like the other quarter of a wavelength. So it's, in essence, you have a half wavelength dipole. Okay. Yes, that's what it does. Radial wires. And the rubber duck. And they talk about the rubber duck. And you know what, as much as, you know, we can laugh at that, it's still, it comes with the little handhelds, and it's good for what it does. You know, for it. And I think Jerry said this earlier, is that, you know, when it comes to antennas or it comes to transmitting, there's nothing perfect. You're making compromises. All right. And the rubber duck, it's as convenient as can be. It's as short as can be. And depending on your application, it may or may not work well.
Your best bet really is that magnetic mount antenna for your car roof. And instead of a handy talkie, get yourself a mobile or a base transceiver. It's not going to cost that much more than a handy talkie, and it gets out a lot farther. You know, 50 watts is a lot better than 5 watts.
Amen. Amen. How are we doing on time? Here's
a few minutes. Well, if people have to leave, they have to leave. But we can put this up on the on YouTube, and you know, anyone who wants to review, they can review.
Okay. So anyhow, this is a great graphic for what a dipole looks like. So a nice center connector. Your coax cable comes up here. Your braid connects on one side. The inner conductor, this thing, hooks up to the other. And then you support the ends with insulators and tied off to, you know, some kind of a support, whether that's a tree or a part of a building or something. Okay. Now, the length of each side is going to be dependent on the frequency that you want to transmit on. Now, now remember, the lower the frequency, the longer the wavelength, so the longer the antenna has to be. But if you're increasing your frequency, then both of these halves have to get shortened, right? Because as frequency increases, the length of the radio wave decreases. Okay. Let's go back here. And like Jerry had said before, you know, starting around 490 feet over the frequency, and then and then you cut to make it resonant, to make it receive best. For ground plane, again, you're doing more like quarter wavelength. So you're going to take 234 divided by your frequency,
which is half of 468.
which is half of
I mean,
460.
yeah, well, it's not magic.
or you can start at 245, which is half of 490. All right, and again, you cut to measure. All right, lengthen and quarter wavelength to 5/8 focuses more signal toward the horizon, which usually improves range. Yes, that's a good thing to know. Okay, so 40 meters, a quarter wavelength width is about 32 feet. Insulating an inductor makes the antenna look longer.
Putting a coil.
A coil.
Actually, there's I don't know if anyone remembers the Slinky toy.
Mm-hmm.
If you can get some metal slinkies, you can actually have a dipole antenna out of slinkies, and it should be quite a length, and you can short out parts of the the slinky to shorten the antenna. But if you're desperate, you use desperate means.
Now, Jerry, when you're saying short out, you're talking about using alligator clips?
Yes.
Yes, okay.
Mm-hmm.
Can I ask you a question?
Sure.
So if you had a 10 meter, it's going to be around, what, 33 feet?
No, a 10 meter dipole?
Yeah.
10 meter dipole would be about 16 feet.
On each side?
No, eight on each side.
But you're saying half wave then, right?
8 is a quarter wave.
Okay.
So eight plus 8.
Well, I mean, so you could tune that antenna, though, to use other frequencies, right? That come along with that. There, a multiple of that 16 feet. I mean, you could go into use. I mean, if you had particular frequencies that fit that, you could use that antenna to anyhow, yeah.
Okay. Well,
I mean,
you got about 3 hours.
Okay.
Tell you about stuff.
I hopefully have a long ways ahead of me to learn all that. But the other thing is with the directional antennas, you put like a rotor up there that you used to call them a rotor a long time ago. I don't know.
Oh yeah.
So then you turn it so that you're aiming at the direction that you may want to talk to someone, or so.
Yeah, it's going to cost you a little bit, but certainly, what Bob Lauer is using is what we historically called the Armstrong method of turning the antenna.
Right. So you have multiple antennas if you have multiple transceivers.
Yes, and actually there is a way of hooking, depending on the kind of antenna. We'll talk about traps and things of that sort. That's electric. Well, I mean, you talked about a coil that electrically lengthens the antenna. There are traps that will electrically shorten the antenna, but actually, you have something like this. It's called a, well, they call it a duplexer. I don't know, maybe it's a diplexer, but you can either attach a transmitter to two antennas, or attach two transmitters or two transceivers to one antenna so they can share it. And if the frequencies that the transmitters are working on are separated enough, say 2 meters and 440, then everybody's going to be very happy. The antenna will work, and the two transmitters will be very happy.
Cool. All right, thank you.
Mm-hmm. Oh yeah, cubicle quads and
right. Oh, by the way, for those of you who have your book, there was one little omission in the manual on page 416. Down. Let me get out of this for a second. Okay. And 416 down in that last paragraph, this one right here. It reads, as frequency increases, the size of the Yagi elements becomes smaller. Okay? That really should read. There was an errata notice sent out by ARRL. Well, I guess this was back in March. Actually, it was back in March of 2019. That really should read, as frequency increases and the size of the Yagi and quad elements become smaller, it becomes more difficult to construct practical antennas. Okay, so it's not just Yagi, but it's Yagi and quad. As the frequency increases, the size of the Yagi and quad elements become smaller.
Unfortunately, I've lived in areas where quads are impossible to keep up. They keep getting blown down.
Okay.
Although a two element quad antenna is equal to in performance to a 3-element Yagi.
Okay. And here's a nice Yagi. This is like my 2-meter beam. My 2-meter. This has more elements. This one will cost you a lot of money, or a lot more than mine cost. All right, and this, okay, this is the quad antenna. And there's another name for this one, which I forget.
Inverted V.
Inverted
No,
V.
no, it's not an it's not an inverted V. That's a different creature altogether. Delta.
It's a delta. It's a delta loop.
Okay. Learn something new every day.
Okay. So on this Yagi, this support beam, okay, that just supports the elements, and here are the elements. On this one, it looks like this. I can't quite tell because I don't see where the coax connects, but it looks like the coax would connect on this one. So that's the driven element.
I've never heard of a 2 reflectors, but it's okay.
Okay. All right. Okay, directional antennas, maximum range contacts. All right. For UHF and VHF. Oh, to avoid multipath. Yeah. The other thing though with VHF and directional antennas is you can also use a directional antenna if you need to try and bounce your signal off a building. These can be helpful for that. Okay, but just like just remember that the difference between the directional antenna and the vertical antenna is that you're going in one direction, and if you're pointing west, don't expect to hear much from the east.
Mm-mm.
Okay, now back at back at very high levels, very high frequencies, you end up using dishes instead of ground plane antennas, vertical antennas, or dipoles, or Yagis for that matter. You end up using dishes. Very high gain. They can be quite small in size, or this one's a honker.
Yeah, what the dish actually gathers the signal, and then since it's a parabolic dish, sort of bounces it into a focused receiver that's maybe a couple of feet from the dish. It's at the center, and it's very, very sensitive. You can use that for moon bounce pretty easily.
Okay, and we talked a little bit about coax cable. There are different types of coax cable. The larger the diameter, the less loss. Also, the larger the diameter, it is a little harder to work with, and it's a little more expensive. The RG58, like I say, is about 20 cents a foot. LMR 400 is $1, $1.25 a foot, depending on where you get it,
Mhm.
whether you have the connectors installed or not. Okay, the larger the diameter, the lower the loss. Loss increases with frequency. So loss due to the size of the cable is more important, and it gets worse with higher frequencies. So the higher the megahertz, the more you got to worry about that. And yeah.
Well, as a standard, if you buy yourself a mobile unit and a magnetic antenna, it's going to have usually something like RG58, which is lossy, but it's a very short length, so you don't worry about the loss that much.
Okay. Okay, and for feed lines, the normal kind of stuff. After a while, the exterior, the rubberized exterior, that'll degrade over time with exposure to ultraviolet light, and of course, you got to keep water out of it.
Some cable can be buried too. I'll pay a little extra for that.
Yeah. Okay. Yeah. Yeah. You do that after you buy your $3,000 linear accelerator. Okay. All right. RG58 is very common. But again, it's much more loss in VHF, UHF frequencies. RG8, much lower loss, particularly in the higher frequencies. And most coax cable has got to be 50 ohms. 75 ohms is something special, I think. Cable, I think, uses that. But
cable, actually, when you get to HF, a dipole, well, dipoles usually have an impedance of somewhere around 72 ohms, which is the same as what you can get from cable. So if you're very friendly with your Comcast guy or whoever, maybe a case of beer or something of that sort, maybe you'll get a length.
Roll you off a foot, a couple of feet.
Yeah.
Okay, connectors. Connectors are interesting things to know. The UHF connector. All right. Years and years ago, they used to call UHF starting way lower than they do now, down near 20 or 30 megahertz. This was pre-war, and pre-World War II anyhow. So what's now called a UHF connector is really very, very common for both HF and VHF. All right, so in this case, UHF really doesn't mean ultra high frequency. All right, then there's this Bnc connector, Bnc, Banet Neil Conselman. This is a quick connect kind of, where's the Bnc? This is a quick connect and quick disconnect kind of thing. It's very common for VHF and UHF. It's a much smaller kind of thing. Yeah. And it's you'll often see these connectors used on handy talkies. Okay.
The older ones anyway.
There's the N connector is just it's a medium-sized threaded connector, just like the UHF. The UHF, they say the PL259, the PL250, that's the plug part, the plug. The SO is the socket where the plug goes in, okay? The N is this kind of the same thing, except it's
heavy duty, very heavy duty.
A medium-sized threaded connector. And then there's the SMA, which is the sub-miniature version A connector, which has some specific uses. There. Where's
it's like this one.
there?
My little Yaesu transceiver.
Okay. All right. soldering.
Bob, do you want me to pick up this stuff next week?
Yeah, would you please? Because what time? Oh God, we're at 9:15 already. Okay.
Yeah. Okay, why don't we do that?
All right. Yeah. Thank you so much. And for those of you who stayed with us, thank you.
Okay.
Hey,
Yeah,
you
send us
learn.
emails. Send us emails if you have any questions.
All right.
Have a great night.
Okay,
All
take
right.
care.
You guys have a great night.
Okay. Thanks.
Good
night,
night.
guys.
Thank you.
Good night, Bob. Good
All right,
night,
thank you.
Jerry.
Good night.
Good night.
Stop recording.